Hi everyone. In this video, we're going to talk about what's called the extreme value theorem. To put this in perspective, we've been working on using the first derivative and the second derivative to find characteristics of the original function. And so if you remember, we were able to use the first derivative to find intervals of increase, decrease, and relative extrema. And then we were able to use the second derivative to find intervals of concavity and inflection points. What we're moving into now is finding what's called absolute extrema or global extrema, which is different than relative or local extrema. Your absolute extrema would mean the highest point, which is the maximum, and the lowest point, which is the minimum. Okay? Now, we're going to start by looking at some graphs. If we're talking about the highest point and the lowest point, it is possible that a function does not have an absolute maximum or an absolute minimum. First of all, let's just think about a linear function. A linear function has no extrema. And that would include relative and absolute, okay? If you think about, let's say, a quadratic function whose graph is a parabola, then the vertex would actually be considered a relative minimum, and it is also the absolute minimum because it is the lowest point on the graph. This function has no relative or absolute maximum because both ends are up, and so your y values are going to approach infinity as x approaches positive and negative infinity, meaning we cannot identify the highest point on the graph. If you think of a cubic polynomial, which would look something like this, this graph has a relative maximum, it has a relative minimum, but it has no absolute extrema because one end is up, one end is down. So as x is approaching negative infinity, y is approaching negative infinity. As x is approaching infinity, y is approaching infinity. So there's no way that we can identify the highest or the lowest point on the graph. Okay, now let's look at these other graphs. In figure 1, this particular graph has an absolute minimum and an absolute maximum. This point would be your absolute minimum, but it would also be considered a relative minimum. This point, which is an endpoint, is the absolute maximum, but it is not a relative maximum. Okay, so that's one key thing I need you to understand, is that endpoints cannot be classified as relative extrema. Okay, because we're not really sure, what's happening on the other side of this point. This could be a turning point, or maybe it's not. Okay, so endpoints are only considered absolute or global extrema. Okay, so this first graph has both an absolute minimum and an absolute maximum. Let's look at figure 2. So this function, again, has an absolute minimum, but no maximum. In figure 3, this graph has no minimum because there is now an open circle here, but it does have a maximum. Okay, so in figure 2 and figure 3, we were not guaranteed that the graph would have both an absolute minimum and an absolute maximum. So I really want you to focus on figure 1 for a minute, because figure 1 is the only graph that has both an absolute minimum and an absolute maximum. So I want you to ask yourself, what do you notice about this graph? Okay? Well, I hope one thing that jumps out at you is, and compare it to the other two graphs. What's different about figure 1 compared to figure 2 and figure 3? Well, I hope one thing you're noticing is that figure 1, the graph is continuous on the interval. If you look at figure 2, well, and let me just say, this is continuous on a closed interval. So notice that at the endpoints are solid, okay? So meaning we're including the endpoints as part of that graph. So this graph is continuous, meaning there's no holes, okay? On a closed interval, meaning that the endpoints are solid, okay? If you look at figure 2 is continuous, there's no holes except at the endpoints. So this we would say is continuous on the open interval, okay? And actually, I could give values to my A and B here. Because based on the graph, we do know that the interval is -1 to 2. And same thing for figure 2. This would be from -1 to 2, but again, we're using parentheses because of the open circles at the end. And then if you look at figure 3, figure 3 is a function on a closed interval, but the problem is it's not continuous because we have this open circle. Okay? All right, so this is kind of leading to the extreme value theorem, which says if f, or a function, is continuous on a closed interval, okay? So this has to be true. The function has to be continuous on a closed interval. Then f has both a maximum and a minimum, okay? All right, so remember the extreme value theorem is what we call an existence theorem because it just proves that the maximum and minimum exist. So then the question becomes, okay, if we know that they're there, how do we find them? So these are the guidelines for finding extrema on a closed interval. So the first step is to find the critical numbers. And remember, we've talked about that in the past. Find your critical numbers. Critical numbers are where f prime is equal to 0 or where f prime does not exist. Then we're going to evaluate f. So this is where you're actually going to find those values of x, but then plug them into the original function, okay? And because your absolute extrema can occur at an endpoint, you also want to plug each endpoint into f, okay? So you plug your critical numbers and the endpoints into the original function. And all you're doing is you're looking for the greatest y value, which is the maximum, and the least y value, which is the minimum, okay? All right, let's look at an example. All right, so we're going to start with a polynomial, which are usually the easier ones. We want to find the extrema of f of x on the closed interval -1 to 2. Okay, so we got to start by finding f prime. And we're just using power rules, so we get 12x cubed minus 12x squared. We're going to set the derivative equal to 0. And we're going to solve for x. So we're going to try factoring. We can factor out 12x squared from each term, which is going to leave x minus 1. Set each factor equal to 0, and then solve for x. So we end up with x equals 0 and x equals 1 as our critical numbers. Okay. All right, so now we're just going to set up a table of values. X, f of x, because remember, we're plugging into the original, okay? Now, we have to include our endpoints in our table and our critical numbers, okay? So I'm just going to kind of put them in order. We have -1, 0, 1, and 2. And all you're doing is plugging these into the original function to find your y value. Okay, so let's see. If we plug in a -1, we'll have 3 times -1 to the 4th minus 4 times -1 cubed. This will end up equaling, because -1 to the 4th is +1, times 3 is 3, and then -1 cubed is -1 times -4 will become +4, which is going to equal 7. All right, we're going to plug in a 0. Well, that's easy. That's just going to end up equaling 0. We're going to plug in a 1. So we'll get 3 times 1 to the 4th minus 4 times 1 cubed, which will end up just being 3 minus 4, which is -1. And then we're going to plug in a 2. So 3 times 2 to the 4th minus 4 times 2 cubed. Okay, 2 to the 4th is 16. 2 cubed is 8. All right, so we end up with 3 times 16, which is 48, minus 2 times 8, which is 16, which ends up equaling 32. All right, so based on our table, 1, -1 is the absolute minimum, and 2, 32 is the absolute maximum. Okay, so, you know, we kind of want to write our answer out a little bit better than that. So we're going to say that f has a maximum value of 32 at x equals 2, and a minimum value of -1 at x equals 1. There we go. And you actually don't have to put absolute in front of the maximum or minimum if, and this is true when you read the questions on the AP exam as well. If the question just asks, find the maximum value, that means absolute maximum, okay? If they don't mean absolute, then it would say relative or local, all right? But sometimes, you know, they won't use the term absolute or global, but if it doesn't say relative or local, then you know that's what they mean, okay? And so, like in our original question, when it said find the extrema, because it didn't say relative extrema or local extrema, we know that they mean absolute, okay? All right, so this gives you an idea of how to find the absolute extrema, but let's look at a couple more examples dealing with some other types of functions. So here our function is 2x minus 3x to the 2/3 power, and we're given the closed interval -1 to 3. But again, in order to find the extrema, we're going to start by finding the derivative, and we are using power rule, so we'll get 2 minus, well, 2/3 times 3 is 2 times x to the, remember we have to subtract 1 or 3/3, so that'll be to the -1/3 power. And we're going to set this equal to 0, but it probably would be easier if you simplify and to change your negative exponent to a positive, we're going to move it to the denominator, and then you could change it back to a radical or not. You don't have to. We can leave it to the 1/3 power. Okay, so then the question becomes, well, wait a minute, how do I solve that? Well, what I would do is I would add the 2 over x to the 1/3 power and set it up like a proportion. Okay, this would be 2 over 1. So that way you can cross multiply. Okay, so then we're going to end up with 2 times x to the 1/3 power equals 2 times 1, which is 2. And then we'll solve for x. So we'll just divide by 2. We'll get x to the 1/3 power equals 1. And then how do we undo that 1/3 power? Well, you just raise it to the 3rd power. Okay, because 1/3 times 3 is equal to 1. So we're just going to cube both sides, and 1 cubed is still 1. Okay, so x equals 1 is our critical number. All right, so then we're going to set up our table of values. X, f of x. We're going to include our endpoints and our critical number. And then we're just going to plug these into the original function. Okay, so to find f of -1. And you guys, you may want to think of this, this fractional exponent. This would be the same as 2x minus 3 times the cubed root of x squared. Okay, that's how you can, change that fractional exponent to a radical, because it might be easier now when you're plugging in. But if we plug in -1, we'll have 2 times -1 minus 3 times the cubed root of -1 squared. Okay, well this is going to simplify to, well 2 times -1 is -2. Okay, minus 3 times, well, start under the radical. -1 squared is 1, cubed root of 1 is 1. Okay, so this will just end up being -2 minus 3, which equals -5. Okay, plug in a 1, we'll have 2 times 1 minus 3 times the cubed root of 1 squared. So this will just equal 2. Again, 1 squared is 1, cubed root of 1 is 1. So this will just be 2 minus 3, which is -1. Okay, and then we're going to plug in a 3. So 2 times 3 minus 3 times the cubed root of 3 squared. Okay. This will end up being 6 minus 3 times the cubed root of 9. Well, 9, it is a perfect square, but it's not a perfect cube. But we're trying to think of what that value would equal. Okay, so you guys, I just went ahead and keyed that into the calculator just so we have an actual y value. Now, because I did have to approximate it, remember you always want to round to at least 3 decimal places. So anyway, we end up with -0.240. So as far as our absolute extrema, -5 is the least y value, so this would be our absolute minimum. And -0.240 is our greatest y value, so that would be the maximum. Okay, so now let's just answer our question. We're going to say f of x has a maximum value of -0.240 at x equals 3 and a minimum value of -5 at x equals -1. Period. Okay. The reason we're writing that out is because, just like when we were drawing our sign charts, on the free response questions, the graders will not use the sign chart as justification. Same idea here. You have to, write out your final answer. Now, as long as you show your table of values in the work, that you use to find those y values, then that is enough justification for your conclusion, okay? All right, we have one more example. Let's look at how this works out with a trig function. The steps are the same, so we're going to start by finding our derivative. Okay, so 2 is a constant multiple. We'll just bring that down. Derivative of sine is cosine. Okay, minus derivative of cosine of 2x. This is chain rule. Derivative of cosine is negative sine, so this will become a plus sine of 2x, but then times the derivative of 2x, which is 2. I'm just going to put that in front. All right, we're going to set this equal to 0. All right, now we're going to solve this equation. All right, the way that this equation is right now, it's going to be kind of tricky to solve. But what we can do to make it easier is we can actually use a trig identity. This is called a double angle identity, and it's sine of 2x equals 2 times sine of x times cosine of x. So we're just going to substitute in place of the sine of 2x, and that's going to allow us to actually solve by factoring. So this will become 2 times cosine of x plus 2, okay, times 2 sine of x cosine of x equals 0. So now this is 2 times cosine of x plus 4 times sine of x times cosine of x. Okay, that one's helpful though, because now if you notice, we can actually factor out cosine of x from each term, and you can even factor out a 2 from each term if you like. Let's go ahead and do that. Let's factor out 2 times cosine of x. Okay, which is going to leave 1 plus 2 times sine of x equals 0. And then we'll set each factor equal to 0. And then we're going to solve each trig equation. So remember, to solve a trig equation, you get the trig function by itself. So this first equation, we'll just divide by 2. And we'll have cosine of x equals 0. And then we're going to use our inverse trig function and our unit circle. Now remember, we're looking on the interval from 0 to 2 pi. So you have to think to your unit circle, where is cosine equal to 0? Well, cosine is the x-coordinate. So the x-coordinate is 0 at pi over 2 and 3 pi over 2. All right, then we're going to solve the second equation. We're going to get sine of x by itself. So we're going to subtract 1 divided by 2. And this will become sine of x equals negative 1/2. And then we'll use our inverse trig function. And then again, we're going to think to our unit circle. Where is sine equal to negative 1/2? Sine is the y-coordinate. And again, if you think of your unit circle, because sine is the y-coordinate, then sine is going to be negative in quadrant 3 and quadrant 4, because you have to go down to plot those points. And we're thinking of where, sine is equal to 1/2. Well, that would be at pi, in quadrant 1, that would be at pi over 6. But in quadrant 3, remember the numerator is 1 more than the denominator, so that would be at 7 pi over 6. And then in quadrant 4, it's 11 pi over 6. Okay, so these are our critical numbers. All right, so we've got a little bit more work to do. We've got to set up our table. And we've got to include our endpoints and our critical points. So we'll have 0, pi over 2, 3 pi over 2, 7 pi over 6, unless I'm running out of room in the table. 11 pi over 6, and then 2 pi. Okay, and then we're going to take these values, we're going to plug them into our original function. Okay, now just to save time, I'm going to show you one of these, but then I'll probably pause the video just because I know you don't want to be here forever. Okay, so let's extend the page. We can start with 0. F of 0 would equal 2 times sine of 0 minus cosine of 2 times 0, which is 0. Okay, so then think your unit circle. Okay, again, this is 0, and the ordered pair is 1, 0. So sine at 0 is 0, minus cosine at 0 is 1, so we end up with this equal to -1. Okay? All right, so I'm going to keep working on just plugging in these x values and finding f of x. Okay, you guys, so I'm back now, and I filled out all of the values for f of x, and again, I got these by just plugging in x into the original function, using my unit circle to evaluate the trig functions. Okay, so now if we look at our results, 3 is clearly the greatest y value, so this would be our maximum. But if you look for the minimum, the least y value would be -3/2, because that's -1 1/2. And it just happens at 2 different x values. Okay? All right, so how do we say that or write our final answer? We're going to say that f has a maximum value of 3 at x equals pi over 2, period. And we'll say f has a minimum value of whoa, what is going on? I got to get extend the page. Of -3/2 at, and it just so happens that that value occurs at x equals 7 pi over 6 and 11 pi over 6. So you'll just include both of those x values. Okay? All right. I don't know if we could have gotten that any skinnier, but some of these problems take a lot of work. All right. So you guys, we're approaching 30 minutes of this video. You're probably tired, as I am as well. Anyway, we'll definitely practice this in class some more tomorrow. Thank you for watching. Have a good night.